All right, good afternoon, everyone. We'll see if you still feel that way about this after the slides I'm going to show you. So, I'm Romain Guy. I work on the Android Toolkit and Jetpack team at Google, and this is Chet. No, I always forget. Chet just quit. I think he said, "I hate France, I'm never coming back." True story. No, he's back. He's in school. For those of you who don't know, he decided to go back to school. It's not something I would do, but he's happy. So, anyway, it's going to be just me today. I'm going to talk about something that I really care about. We're going to talk about Jetpack Compose optimizations. We're not going to talk about the kind of optimizations that you've heard about in other talks or articles, how to use remember, how to avoid recomposition. Those talks and articles are great, and besides, I wouldn't know how to tell you how to do it better. Instead, I'm going to talk about optimizations that we've done inside of Jetpack Compose to make it faster on behalf of your app. So those optimizations, the goal is mostly to try and teach you, hopefully, some programming techniques. You may not be able to use those techniques as is in your application, but hopefully, they will be helpful to you someday at some point. So, first I want to chat about how do you find things to optimize in your app. And this slide is going to look really silly. First, you profile the app. There's a number of ways of doing that. The way I like to do it is to start, surprisingly, with a memory profiler. I like to look at allocations and find places in the code where we're allocating objects where I feel like we should not be allocating objects. Because usually what this tells me is that when we wrote the code, we were not paying attention to performance, and the fact that we've left allocations probably means that we've left other things as well. And so far, it has steered me right. So then when you look at that code, question it, right? Like, try to investigate what you're seeing. And again, you start with the allocations, and you start looking around the code, and you find, maybe algorithms that could be faster or simpler. Maybe we're using the wrong data structure. Or maybe you could use one of those techniques that we're going to talk about. And more importantly, at the end, please write a benchmark for two reasons. One, to make sure that the code that you're writing is faster. I've been writing optimizations for Android for 17 years now, and it's still almost every other optimization I write turns out to not do anything or to make things worse. So you don't know until you try. So write a benchmark. And the second aspect is that once you have a benchmark, you can make sure that you're not going to have regressions. So for Jetpack Compose, and in general in Jetpack, we have a number of benchmarks that we run in CI. And so every time we make changes in the code base, if there's a regression going up or down, we automatically file a bug, so we can check what happened, we can fix it, or we can make sure that if performance actually improved, it was on purpose. Sometimes we have surprises that are positive surprises, but it's good to double check. So to do all that work, you'll need a couple things. First, you need hardware. You need a phone. You never do optimization work on the emulator. It just doesn't work. And actually, if you try to use the Jetpack benchmark library, it won't let you run a benchmark on the emulator because we can't ascertain that the numbers will be correct. So you have to use a phone. Then I highly recommend to get a fridge. I know it sounds ridiculous, but I use it regularly. When you run a lot of benchmarks and your phone gets hot and the numbers get weird or the benchmark library tells you that your phone is too hot, you go shove it in the freezer for a couple minutes and then you can resume your work. If you don't have a giant fridge, this is the kind of fridge we have in the US, you can get a bag of ice cubes, a bag of frozen peas, whatever you have. I also use from time to time a hand fan that also works. Like while I'm running the benchmarks, I just have the fan blowing on the device. Again, I know it sounds silly, but it's extremely useful. And in terms of software, so there are a few things that you will need. First, so profilers, right? We have a number of profilers. There's been a lot of talks. We have a lot of documentation on developer.android.com. This is the new UI for profilers that's in Koala, whatever is the latest Android Studio Canary. Makes it easier to find all the profilers in the same place. Like I said, I like to start with the memory allocation tracker. But of course, you can use the method tracing or the system trace. Depends on what you're trying to achieve. Then go look at the Jetpack benchmark libraries if you haven't done so. Writing a benchmark using those libraries is very simple. But more importantly, what the library will do for you is it will talk to the device and tries to set up your device so that multiple runs of the benchmark will lead to stable numbers. There's nothing worse than running a benchmark and you think that your optimization doesn't do anything, and then you run the benchmark like an hour later and your device is cool, and now you're seeing that it's going faster. So the benchmark libraries, for instance, will try if your phone is capable of it. It depends on the system image, if the device is rooted or not. We're going to try to lock the clocks. We're going to make the device run slower than a normal device, but we're going to be able to sustain the speed. There won't be any thermal throttling, and that way the numbers will be very stable. And it does other things. It disables system animations. It tries to prevent other things from happening while you're running the benchmark. So go use the benchmark libraries. They're extremely helpful. And they have another use case that we'll talk about at the end. Then we're going to look at, in a little bit, at a piece of software called Kotlin Explorer. That's a tool I wrote that's available on GitHub. It lets you easily look at the output of the Kotlin compiler, and more importantly, at the code that actually runs on your device. And last but not least, one of the few cases I have for AI turns out that when you read assembly code, assembly can be a little bit painful to read, and feeding that to an AI, the AI don't trust what it says about what the algorithm does, but it will be able to tell you line by line what each instruction does. And assembly can be tedious, and it's very annoying to have to go read the manual from ARM about every instruction you don't understand. Use an AI, they will be able to tell you line by line what the code does. It looks scary, but once you do that, it's very easy to follow along. All right, so let's look at the first optimization. So here we have it's actually a benchmark. So we have a simple loop. We are looping over all the pixels in a bitmap, and we're just looking for the pixel that have the largest red value. Can any one of you tell me what's wrong with that code? You can just raise your hand, I'm not going to check, so, okay, none of you. All right, so pay attention, there's going to be a short animation because the fix is super easy. We're just going to swap the X and the Y in the loops. Why would you do that? So here's a benchmark running on a Pixel 2. When you benchmark, also, I highly recommend to try and use, hopefully, the slowest phone that you expect your users to be using. So I still have a Pixel 2 from 2017. No, not the worst phone in the world, but by today's standard, it's a pretty low-end phone. So it gives me results that are more interesting than using the latest Pixel 8, for instance. So the original code for that benchmark was taking 20 million nanoseconds, and by just swapping the X and Y, we're down to 4 million nanoseconds, right? So that's over 4 times faster to run the code by just swapping those two lines. And we're going to take a look at why. And that code, by the way, I found it in the Jetpack Compose code that was running our golden screenshot test. So by just swapping those two lines, suddenly all our tests ran a lot faster, which is really nice. So here's the reason why. So here, we're going to take a look at the two CPUs that are in the Pixel 8. So Pixel 8, every phone out there right now, they have what's called a big little architecture. They have two types of CPUs inside the phone. And it's important because the CPUs are very similar, but they have some differences. So if you look here, the Cortex A715, that's the big core. So those are the more powerful CPUs. Each core has what's called an L1 cache. That's a memory cache where the CPU is going to store some amount of memory. And typically, depending on the configuration of your phone, on this particular type of core, it's going to be between 32 and 64 kilobytes of RAM. Most of the time, I think on the Pixel 8, it is 64 kilobytes. Then you have the L2 cache. So when the CPU tries to read memory from data from memory, it's first going to look at the L1 cache. If it doesn't find the data there, it's going to look at the L2 cache. There's an L2 cache for each core, and the L2 cache is between 1/4 and 1/2 of a megabyte. So it's a lot more data, but of course going there is more expensive. And then finally, if we can't find the data we're looking for in the L2 cache, we're going to go through the L3 cache that's shared between all the cores. So if you have multiple cores doing work, all the cores putting data in the L3 cache is going to affect the other cores running. The little core, on the other hand, it's very similar, right? You have an L3 cache, you have an L1 cache, and an L2 cache. But the difference is that the L2 cache is shared by the cores inside the complex. So you may have two CPUs sharing two cores, sharing an L2 cache. You don't need to know all the details. The point of those two slides is to let you know that this is the basic architectures in terms of memory of a CPU. And it's important to know that not all CPUs are the same in terms of the cost to access the data. So the Pixel 2, for instance, might be different. The size of the caches will be different, so you're going to get different numbers. So if we go back to our example of the bitmap, when we want to iterate over the pixels, if we first try to read the first pixel, right? So in memory, you can see here there's a grid to represent the bitmap, but in memory, all the pixels are going to be side by side. They're next to each other in memory. So we're going to try to read the first pixel. Because the data is not in the L1 cache, we have to go fetch that data from RAM. And the way the CPU does that, it fetches a cache line. So it takes 64 bytes at once and keeps that in the cache. The idea is that you fetch all that data, and if you happen to read data that's next to the one that you just requested, it's basically going to be free because it's already in the cache. So here we pre-populate in the memory cache the data that we may need, but because we are iterating the first pixel of the pixels of the first column first, when we request our second pixel, the memory is not in the cache. So we have to request another cache line. So we go back to the RAM, all the way to the RAM, we fill our cache line, and we just don't use the first one. Then when we reach the third row, we run into an issue. Like I said, the L1 cache only has like 32 or 64 kilobytes of RAM, which is not that much. So at some point, if you keep filling the cache that way, you're going to have to discard the memory that you had previously fetched. So by the time we reach the second column, none of the data that we used to have in the cache is still there, and so we have to do another cache fetch and go another time to memory. Now, if we compare that to the modified version of the code, where we go row by row instead, when we fetch the first pixel, it's not in memory, we're going to fetch a cache line, and then for the second pixel, the data is in the cache, we don't have to do anything, it's super fast, next pixel, it's in the cache, and so on. And that's why, like, when you look at data, when you process a lot of data, you want to make sure that your access to the data is linear, right? That you try to always read data that's next to the one that you just read. And as you've seen, it can make a huge difference in the performance of your algorithms. So if you're reading files, if you're even talking to a server, every time you're dealing with big buffers of data, make sure you're doing that. All right, so now we're going to look at this Kotlin Explorer thing. Let me find... Where did I put it? It's right here. Sorry, it's on the wrong screen. All right, so to use this tool, it's pretty simple. You can type Kotlin code on the left side, and then when you press here, compile and disassemble, it's going to take that code, compile it to an APK, and show you the DEX bytecode. And then if you have an emulator or an Android phone connected to your computer, it's also going to show you the ARM assembly code. So on the right side, this is the actual CPU code that will run on the device. And this is the most interesting bit. So if we look at this example here, we have a very simple function, takes an integer, and returns the sign of that integer. So it will return 1 if it's positive, 0 if it's 0, -1 if it's negative. And you can see the way it's translated into DEX bytecode is by calling a static function called mathkt.getSign. And then, the ARM assembly code, we're not going to go through all of it, but basically that's what it does. It invokes the static function. Now, if we turn on R8 and we recompile this code, we're going to see the difference. There's no more static function. R8 just inlined the function call. So now what we have is a series of if statements. And you can see, by the way, when you click an if or a goto in the code, it's going to show you where it jumps if the condition is taken. And you can see now that in the ARM assembly code, there's a series of comparisons, and cset, it's kind of like a branchless if statement. But basically, the function is gone. So this is the tool I use a lot to figure out, okay, what is the code we're actually running? And there are some surprises. So now if we look at the same function, but for floats, we're going to disable R8. You're going to see something else that's interesting. So here, again, we get the sign of a float. In the DEX bytecode, we invoke a static function. But when we look at the ARM assembly code, there's no function call. It's all comparisons, if statements, moving values between registers, and doing masking. That's because in Art, there's something called intrinsics. So intrinsics are APIs that the VM knows about. And in this case, it's the java.lang.math.signum. That's a function that the VM understands. And instead of calling the function, it will replace the function directly with its own hand-optimized assembly code. So this is what you're seeing here. And here, like if you were to enable R8, it doesn't matter because R8 has nothing to optimize. The optimization is done by Art itself. And if we look at the last example, you're going to see why optimization work can be very difficult sometimes. So here we're simply calling a max of, so we want to find the maximum value of 4 different integers. Because that function in the Kotlin standard library takes a var args, we can see that in the text bytecode it's creating an array, and then it's invoking a static function, kotlin.comparison.something, which leads to a ton of ARM assembly code, pretty complex function. We can see there are allocations there. So we're just trying to find the maximum of 4 values, and suddenly like we're allocating arrays, we're calling functions. It's a very expensive process. But if we were to turn on R8, some magic's going to happen. So R8 is going to inline, effectively, it's still creating the array, but now it's inlining the function max of, and there's a goto here. You can see it's pointing back up. There's basically a loop. It's looping over the values of the array. And what art is capable of doing is that it sees it's a for loop that loops only over 4 values. So it's discarding the loop, it's discarding the array, and suddenly like the code is completely optimized, right? So there's a huge difference. Just the act of turning on R8 will give you a huge performance boost. Anyway, so that's what Kotlin Explorer can do for you. It's very, very useful. And we're going to look at some examples. So let's talk about the offset value type in Compose. If you've used Compose, I'm sure you've used offset. It's a class that only has an X and a Y. The way it's implemented, it's a value class in Kotlin, so we actually store only a long. So the X and Y floats are stored inside the long, right? A float is 32-bit, a long is 64-bit. We can store both of them in a long. That way we don't have any allocations. The class doesn't exist at runtime. But if you look at the original code, for the X property, the getter first does a check. So check in Kotlin, it's part of the standard library. You give it a condition, and if it fails, it throws an exception with the string that you have. And then we do the actual work of finding our float out of the long. Now, here's the fix that we've done in Compose. We replaced the call to check by something called check precondition. Check precondition is not part of the standard library, and I'm going to show you what it does. But the difference between the original check and the new check precondition is going from 124,000 nanoseconds down to less than 100. So that's a 1.3 times speed up by just making that change. And let's look at the change. So this is the implementation of check inside the standard library. It takes your Boolean, it takes your lambda. There's a contract, you can ignore that. And then there's just a simple if statement, right? It says, if the Boolean is false, we invoke the lambda, and we throw an exception. The function is in line, so the compiler is not going to allocate a lambda. It's all going to be in line in your code. And this is what the ARM assembly looks like. You don't have to try to understand what it does. It's just, the point here is that there's a ton of code. And if we were to highlight the part that's only about the exception, everything in red here is only that one line of code to throw the exception. But most of the time, you're not going to throw the exception, so probably not a big deal. Now, here's the version that we use in Compose instead. So same exact implementation. The only thing we did was take the throw to throw the exception, and we moved it to a separate function. Right? Like the code is doing exactly the same thing. Actually, it's even worse because we introduced a function call. But if we were to look at the ARM assembly code that actually runs on the device, we go from this to this. We went from 47 down to 26 instructions. And if we look at the code that actually does the throw, so it's just calling the function, it's only those few lines at the end. So the reason why it makes everything faster, because again, most of the time you're not going to throw an exception, so it shouldn't matter that we reduce the code that we never run. But if we go back to the diagrams of our CPU, for the memory caches, there's a cache for the data, so the L1D cache, but there's also a cache for the instructions, like the code you actually run on the CPU. So what we've done is, by shortening the code, we put less pressure on that cache. So when we run our code offset as part of the layout system or the measurement, the CPU can store more code in memory without fetching the L2 or the L3 or the RAM, and therefore can go a lot faster. All right, so now let's look at the offset class. I really like that class because it's a really stupid class. It's just an X and a Y, and yet we were able to make so many optimizations in there, which is ridiculous. So we have this X getter, right? Like we have this X property, and you can see at the end we say return unpack float 1, and we unpack the float from the long. It's a top-level function. Best practices would dictate that we should put that in a companion object to have some namespacing so that we don't pollute our root namespace. So let's look at the implementation. So this is the function, it's in line. It just calls another function. It doesn't do anything very interesting, like it doesn't really matter what it does. And here's the same exact thing if we were to use a companion object. So it's the same exact code. All we do is that we move it to a companion object. At the call site, not very different, right? We call the function, or we call the function except on the companion object. Now, if we look at the Dex bytecode, on the left, the top-level function, there's an invoke static, and then we return the result. And on the right, it's almost the same. We get an object, so we get the companion object instance. It's a static instance. And then we do an invoke virtual instead of an invoke static. Virtual dispatches are a little slower than static dispatches, but it doesn't matter that much. So, should we care? The way to answer that question is to go look at the ARM assembly code. So that's the top-level function. That's all the work you're going to do. That's 3 CPU instructions. And actually, I think one of those, like the move in the middle, is actually useless. And this is the version with the companion object. If you look really hard, those 3 lines that you see on the left, you can find them on the right. So the work is the same, but everything else around, it's just because you're calling a method on the companion object. And it's because it's a static object. So because you're accessing a static instance, the VM has to guarantee that the class has been statically initialized. So there's all that code around to go fetch the value, go read in memory, check the initialization state, and if it's not initialized, it has to jump, call extra functions from art, and then go back to your code. And it goes back to what we were saying just earlier, right? Like, it's not, so those are instructions that we're going to execute on top of adding more code, but adding more code is going to put more pressure on the CPU cache, and it's going to be slower. And so by getting rid of by making sure the function is a top-level function instead of a companion object function, we go from 136,000 nanoseconds on the Pixel 2 down to less than 100. So once again, we're going 1.4 times faster by just doing that. It's basically free. All right, so let's look at offset. Like I said, I really like this example. So offset, it's a value class, it takes so long. The public constructor is actually a top-level function that takes an x and a y. And you can see here it calls another utility function that packs the x and the y inside the long. That's where we do the actual work. The way we store everything in memory, you have a long with 64 bits. You can count them if you want. There are 64 bits here. And in the top 32 bits, we store the x. And the bottom 32 bits, we store the y. Nothing particularly interesting. But from this encoding, we have to implement all the functions that are on the offset. One of them, for instance, we have things like to multiply offsets together, to add offsets, to find the distance from an offset. We have one that's called unary minus. And that's a good example of a technique called SWAR. So unary minus, we just want to take the negative of the offset. So the way we do that, right, like it's pretty obvious. We unpack the x and the y. We take the negative value of the 2 floats, and then we repack the offset before we can return it. But there's a much more efficient way of doing that. So it's called SWAR, and it means, it's a horrible acronym, because it's an acronym within an acronym. It means SIMD within a register, which means single instruction, multiple data within a register. So SIMD is the ability to process multiple values at the same time. If you've heard on PC of MMX, AVX, SSE, on ARM, if you've heard of Neon, those are instruction sets that, for instance, you can give them 4 floats and say, give me the square root of those 4 floats, and it's a single instruction. So the idea of SWAR is to do this kind of stuff, but without using special instruction sets, using only what you already have, in your typical CPU. And that's what we're going to do this unary minus. So if we look at how floats work, so we have 32 bits. There are 8 bits that are used to encode what's called the exponent. We have 23 bits that are called the significand, and I'm not going to tell you what they do and how they work. What we're interested in is that one last bit at the beginning, and that's the sign bit. When that bit is set to 1, the value is negative. When that bit is set to 0, the value is positive. So all we have to do to negate an offset is flip those 2 bits, right? Like we don't need to do anything else. So now we can rewrite our function to do this instead. We just XOR our long with like a magical constant that has only 2 bits set, and that's all. And what the code looks like, so if you look at the assembly, we went from this, where we do a lot of work, to that. And I don't even need a benchmark to prove that that will be faster. Of course, you can't always do this, right? But like this technique is actually a pretty common one, and we use it in other places. So parsing strings. When you load a vector drawable, we have those SVG strings where we have a lot of floats encoded as ASCII. So let's say we want to parse this number, this 1234.0. The regular way of doing this would be to iterate over every character in the string and say, is this a digit? Is this a digit? Is this a digit? And as long as it's a digit, we keep going and then we can parse our float. But we can do better than that. We can take 4 characters at the same time, because in Java and Kotlin, 1 character is encoded as a short, so it's 16-bit. And turns out that in a long, you can store 4 times 16 bits. So we can put 4 characters inside a single long value. So we're going to take our 1, we're going to put it in the lower bit of a long. So 31, that's because the ASCII value of 1 is 31 in hexadecimal. Then we're going to put 2, so that's 32, then 33, then 34. So now we have a long. So what do we do with this, right? We need to check, are those 4 characters numbers? And we know they're numbers if their value is greater than 0, greater or equal, or if it's, and it's less than or equal to the value of 9, right? Like the ASCII value of 9. So the way we do this is that we construct another long that contains the magic value 30, 30, 30, 30. 30 is the code for 0. So if we subtract the 2 numbers, if we still have a positive value, that means that the character is more than or equal to the character 0, right? So chances are it's a digit. So in our case, because it is made of 4 digits, we end up with this 1, 2, 3, 4 inside the long. If it didn't contain digits, for instance, here I have like a plus. So the plus, remember, it goes on the right, so the value is 2b. If we subtract 30, we're going to get this number like FFFB. And the key here is that the top bits are set to 1, right? So one of the top bits set to 1 tells us that this value is less than 0, so it is not a digit. And then we do something similar to check if it's less than or equal to 9. So the way we do this is we add this time, instead of subtracting, we had a magic value 46, because any value greater than 9 where we add 46, we're going to get a value where the top bits are set. We're not going to go into the details, but same thing, right? If we had A123 instead, A is 61 in hex. So if we add this magic 46, we get a value where the top bit is set that tells us this is outside of the range of the digits. So once we've gotten those two values where we've subtracted 30 and we added 46, we can do a bit more binary magic. We can basically test if the top bits are set. And if none of the top bits are set, we get 0 as the result, and that tells us that we just parse 4 digits. And that's the code that's actually used in Compose. It does exactly what we described in those slides. There's a bit more magic at the end to get an actual number as an integer. There's a magic multiplication. But if we ignore that, just doing it this way, instead of parsing character by character, we were able to improve the performance of parsing vector drawables by 10%, which is not negligible. All right, so offset, those 3 techniques I showed you and a few others like this, in the end, when we started with the original offset class that was written, the way you write normal Kotlin code, if you looked at the ARM assembly code, we had 1,300 instructions. And after all this, we were down to 650 instructions. So we removed half of the code in a stupid class that only has an X and a Y. So, makes for smaller APKs, but also they go faster. And what's interesting is because we have all those benchmarks, once we've made the changes, like a bunch of our layout benchmarks came back saying like, yeah, everything got faster. Because this is a class that's used everywhere in Compose, right? I'm sure in your own code, you've created a ton of offsets. And every time you start doing operations on offsets, like, you add them or you subtract them, like we multiply the amount of work that we're doing. All right, so let's talk about data structures now. I feel like all of us think there are only 2 data structures in the world. There's hash maps, and then there's lists. And that's close to being true. But in Kotlin, that's the way you create a hash map, right, most of the time. You call mutable map of, you have a hash map, we don't need to care about what the hash map is. It works, it's great, it's fantastic. If you look at the code base of Compose, you would find that everywhere. The recomposer, actually, the slot table that I'm sure you've heard of, relies on hash maps a lot. And it's a very important data structure, so we want it to be as fast as we can. If you look at the implementation of mutable map of in the Kotlin standard library, you will see that it always creates something called a linked hash map. And linked hash map has an interesting property that I understand why they picked it. I actually don't like that this is the default. A linked hash map will guarantee the order of iteration. So if you iterate over all the values in the hash map, you will iterate them in the order that you've added them. I think it breaks the abstraction, but anyway, that's not the conversation for today. So let's look at how the linked hash map is actually implemented. So there's an array of nodes. I'm sure you've learned about hash maps, but basically those are the buckets, the hash buckets, where we start the linked list for all the values. So there's an array of nodes, and every node is an instance of something called linked hash map entry. And a linked hash map entry contains all those fields. It has the key, it has the value, so far it makes sense, it has the hash code of the key, and then it has 3 pointers. It has before, after, and next. I don't know why there's an after and a next, and I've never seen next not being null, so if you find the answer, like, please let me know. There's a comment in the code when you look at linked hash map, it says something that it's for compatibility. Either way, it's there. So there's a lot more data, right, than what you put in the hash map. And it gets even worse. Sometimes your hash map, depending on the quality of your hash codes, it switches to a different data structure internally, and suddenly your nodes, instead of being linked hash map entry, they become tree nodes, and they add all those fields. So now, and again, I'm very confused about that, there's a before and an after, but there's also a left and right, and there's also a next and a previous. I don't know if they point to different things. Again, if you understand it, please let me know. I didn't want to spend the time understanding. But the point is that those are pretty heavy objects, right? If you're storing things that are small in your hash map, like an integer or a Boolean, you're going to have a ton of memory overhead just because of the heavy data structures. On top of that, those linked hash maps, they have one small flaw that I really don't like for high-performance code. So most of the time, it doesn't matter, right, like as always. But if you're writing layout code, measurement code, drawing code, parsing a file where you want things to go fast, every time you insert something in a hash map, it has to create one of those nodes, one of those linked hash map entries. So you allocate every time you put something in the hash map, which of course can lead to garbage collection and just more memory usage in general. And then when we want to iterate over the data, this is something that we do a lot in the slot table, in the recomposer, in Compose. You're going to have a ton of cache misses, right? Like those are all objects that can be anywhere in memory, and just reading them all is probably going to be bad for the caches. And the reason for that is like the linked hash map has a head. There's a pointer to the beginning of the list. So we have to read that. That will give us a pointer to an entry. Then we have to read the key, the value. Then we have to read the pointer to the after, right, to the next node. But that node can be anywhere in RAM, and we're probably going to have cache misses. So instead, in Compose, actually in AndroidX.collection, as of version 1.4 of AndroidX.collection, there's a new type of hash map called scatter map. We try to follow the existing API, so you can call mutable scatter map of. And the way it's implemented is really simple. There's an array of keys, there's an array of values, and then we have another array called metadata. That one is a bit weird. It's an array of longs, but in a long, we store 8 bytes, and every byte is the metadata for one entry. So it's 8 times smaller than the other two arrays. And that's it. There's no objects, nothing else. So when we want to iterate over all the instances of all the keys and values in the map, what we have to do is like we read a long in the metadata, we read the value, and we read the key, and we're done. And the cool thing is because those are arrays, remember like the way the caches work, the L1 and the L2 and so on the CPU, the next items will already be in the cache. So as we go through the array, it's going to be blazing fast. So memory usage, we go from 32 to 49 bytes of overhead per entry in the map, down to 1 byte of overhead in the map. So we save a lot of RAM. And then if we compare performance, so to insert elements, not only do we not allocate memory, but we are like 1.7 times faster. Removing elements is a bit slower because we have to do a bit more management. And iterating over all the elements is 1.8 times faster. The thing is, because this is a benchmark, this is actually the best case scenario for the linked hash map, because the benchmark just allocates all the entries we want to put in the map, so they will all be next to each other in memory. in a real application, what's going to happen is that, because of the GC, because you're allocating memory at different times in the app, there will be a lot more cache misses. So this is the best that the linked hash map will do. But the scatter map will have constant performance across the lifetime of your app, so you're always going to get the same numbers no matter what happens. We also use techniques like that SWAR technique, right, where we try to do multiple operations inside a single value. We use the same technique. So I told you that we have those longs for the metadata. The reason we do that is if we need to find an empty slot in the table, or if we have to deal with collisions, we can actually test 8 entries at the same time. So here I'm just going to show you real quick. We're not going to go into details, but we have 1 byte per entry. When a byte is set to 0x80, it means this entry is empty in the array. We can put something there. So when we're looking for an empty slot in the table, we can look at 8 bytes at a time and quickly find a slot that's empty. We don't have to iterate over 8 slots. Couple more examples of things that we've done that seem obvious but definitely pay off. Don't repeat yourself. So this is typically the way. I was showing you the vector drawable. To parse the vector drawable, there's a lot of floats, right, that we have to parse. Unfortunately, the way you parse a float in Java or Kotlin is extremely frustrating to me because you call string.toFloat. What that means is that the string must contain a float that's valid. So when you write parsing code, you first have to yourself parse the string, and when you found a float, you tell the float parser, hey, can you parse that float? But you just did that. So we wrote our own float parser. I just spoiled the result. But we wrote our own parser called nextFloat. And the way this works is that you give it a string, you give it an index at which you want to start parsing inside the string. And what it returns is it returns you 2 things. It returns you the float that it found, and it returns you the index after which you can continue parsing. Right? It tells you where it stopped parsing. That means we never have to allocate substrings, and we don't have to do the work twice. So as a result, the vector drawable parser got 20% faster by doing that. Another one, I won't explain the code. If you're interested in that, we left a comment that's 100 lines long in the source tree that explains what the hell this does. The point here is that if you have to do math, right, like for graphics or whatever reason, like it could be like sensor fusion or whatever it is, use approximations. This is an approximation of the cubic root function that we use a lot when we interpolate colors. The way we do the interpolation, we go through a color space that requires us to do cubes and cube roots. We also use it when we apply the interpolation curves for animations. We use cube roots a lot. So the idea was like, okay, can we find an approximation? This is the same idea if you've ever heard of that story. Quake 3 had this magic way of doing a fast square root. This is the same exact technique, except derived for the cube root. The point is, we have this approximation that's actually pretty good. I put the error at the bottom in case you care, but it's twice as fast as the normal cube root. For interpolating colors, it's 10% faster by doing it this way. And when we execute animations, it's 20% faster. So that's a lot of techniques. I'm sure they are scary. We showed you assembly code. It's not things that we're going to use every day. But so before you do any of this, I'm going to ask you to do 3 things. First, please update Compose. And we have the numbers. A lot of you are on old versions, so I'll show you why you should update. So this is the time it takes to run. We have this simple app called JetSnack. This is the time to get to the first pixel rendered on I forget the device. So 52 milliseconds. That was with the version of Compose that we released last summer. In October, it went down by 10 milliseconds. In March, it went down by almost another 10 milliseconds. And in the version that may come out in May, it went down by another 7 milliseconds. So if you just update Compose, your stuff's going to get faster because we're doing all that crazy, stupid work that probably scared a lot of you. So you don't have to. So please update Compose. And if you run into trouble, please come talk to us. We'll fix everything. The techniques I showed you are, they're very targeted techniques. They're super low level. We've done a lot of other things. For instance, we rewrote the slot table to be faster. Or we do something called group elision. Now we have the optional strong skipping mode that will give you another 20% of performance if you turn that on. And we will turn it on by default at some point soon. Next, what you can do is to turn on R8. If you're not using R8, we've seen an example of what R8 can do for you. But on average, right, like not on average, but in general, what we expect, the kind of performance improvement we expect, and it's going to vary from app to app, so it can be more, it can be less, but we expect about a 30% startup time improvement by just turning on R8. So turning on R8 can be difficult sometimes if you rely on a library that's not R8 compatible, but please go talk to the authors of your dependencies to make sure they enable you to use R8 because it makes a huge difference, especially for Compose code. R8 has some optimizations that clearly target Kotlin and Compose, and you're going to do yourself a huge favor. And also your APK is going to be a lot smaller. Then use baseline profiles. Baseline profiles are a way to tell the Android system how to compile the app when you install it on the device. It's not that way you're going to avoid using the interpreter or using the JIT for the hot path in your app, right? Like your app's going to behave faster, sooner. Again, results may vary depending on your app and how you've built your baseline profile, but you should expect around 30% improvement just in startup time because you're not going to be running the JIT. So do that. And similar to baseline profile, you can use something called startup profiles. So what that will do, we're going to use the startup profile to have an idea of what is the code that your app needs at startup. And we're going to reorganize the APK, we're going to reorganize the DEX file so that the code we need at startup will be, it's kind of like the L1 cache. We're going to put all the code we need at startup close to each other so that we don't have to wait for the disk or for memory. And so that's it. So once you've done those three things, then you can worry about doing all that like bit stuff hacking that I was showing you. And if you have questions, I'm sure we can take a few questions before I hand it over to the organizers.